Hello friends, so in this video I will discuss about the characterization of sensor in test beam data analysis. This picture is from this publications of this year, in which I am one of the main author for this publication. So here we have a 6 reference plane based on Alpine sensor used in the run-3 data collection of the Alice experiment. So you can see we have a 6 reference plane 0, 1, 2, 5, 6, 7, and then we have a trigger plane based on the APTS source follower, and this is DUT, which is basically detector under test. So here we want to characterize this detector, which is basically APTS op-amp. So here we want to characterize this detector for the spatial resolution, detection efficiency, and also for timing performances. Since we want to evaluate the timing, so we need a timing reference layer. In this case, as already mentioned, that we have a 6 reference plane of Alpine sensor 0, 1, 2, 5, 6, 7, and in this particular analysis we also use the APTS source follower in the tracking, and these 7 layers are used for the track reconstruction, and then we perform the DUT analysis, detector under test. And these are the analysis steps in the Corribraken software. These are inbuilt in the Corribraken software. So we have a first step, create mask, but it basically allows to select a good region, to select a good event. So basically we select a good pixel fired. We basically avoid the noisy regions in this case. This is also known as the region of interest in this particular software. And then we perform the pre-alignment. So we have the several layers 0, 1, 2, and you can see there are several detector layers. So we perform first pre-alignment. In the pre-alignment we use one of the plane as the reference plane, and then we evaluate the offset of each plane with respect to this reference plane. For example, if you use 0, then we evaluate the offset of each plane, and then we apply the offset correction in the first step, and this is known as the pre-alignment. And then we perform the alignment. After the pre-alignment we perform the alignment, in which what we do, we basically reconstruct the track, full track using these layers, and then we apply on this, for example this layer we apply the rotation translation. So we rotate, we translate in the x direction, y direction, and z direction using the parameterized equations, and we also rotate them in x, y, z directions, so that we get the optimal position that gives a good chi-square. So in the alignment we align all the layers 0, 1, 2, 3, all the layers we align them, and after the alignment we basically do the tracking. So we basically reconstruct the track using these reference layers as well as this APTS source follower, and then we perform the analysis. So in the analysis we evaluate the spatial resolution of the sensor. This is our sensor under test, so we want to evaluate the spatial resolution. So after the full tracking we evaluate the residuals on this plane, so that is known as sigma residue. We can evaluate the residual, and then we can take the sigma of these residuals. And then we also have the tracking resolution at this plane, so we know how much is the tracking resolution at this plane. Then we can evaluate the spatial resolution using this formula, and that's what we are interested, and this we evaluate as a function of the different detector threshold. And then we also evaluate the detection efficiency, basically how many clusters are associated with the detector with the reconstructed tracks, and we can also quote this detection efficiency for this particular chip. And for the